This tutorial is about the FTCS method for parabolic partial differential equations. So let's take the example. And in our example, we have differential equation partial u partial t equal to partial squared u partial x squared. And we will solve this problem with h equal to 0.1 and k equal to 0.001. We have a center difference form for space. So second derivative should be defined with this relationship. So ui plus 1j minus 2uij plus 2u plus ui minus 1j over h squared, and with its associated error term, which is of second order. So here the I index refers to x and j index refers to the variable t. For t, we use the forward difference formula. So again, a partial derivative uij plus 1 minus uij divided by k. K is the step size in time. So we march forward in time domain. So if we look at the stencil for computation, so xi minus 1, xi plus 1, and we have these 3 points which are used to compute a derivative at the central point. And also when we use the derivative in the time with reference to ij point, so we encounter ji plus 1, tj and tj plus 1 points. So the equation that we will develop, that will be written in explicit form for this point that has been encircled, which is xi tj plus 1. So we will represent this value by uij plus 1. So if we define lambda value as alpha squared k over h squared, so in our selection of h and k, this value turns out to be equal to 1. So we can write the explicit equation. Now let's look at the boundary conditions. So we have the first boundary condition, which is at x equal to 0, and for all times it is 0. So how we are going to solve this one in explicit form? So I have developed x-axis as the vertical as varying from top to bottom. So it means I have to rotate this figure in the clockwise direction. Okay. Not here. And this point, this is the point. Yeah. So now t-axis is moving, is looking towards the right side, and x-axis is looking towards the bottom. So now let's define the boundary conditions. The first boundary condition, u0 t equal to 0. So when x is equal to 0, and for all times the value is 0. So the time axis is varying over here, x is 0, so I have selected x equal to 0. So the value of u function is 0. Let's see the other boundary condition. Is u1 of t, it is equal to 0. So at the other boundary, when x is equal to 1, we have the values equal to 0. So I developed earlier the frame for you. Now the initial condition, ux0, when t is fixed, we have the value sine pi x. So when t is equal to 0, as I have shown here, it is ux0. So for all points, we have a value sine of pi x. So let's generate these values. So I write here equal to sine pi times, well, in Microsoft Excel it should be written as pi with the parentheses and pi x. So this value has been generated. This is from the initial condition. For all for x values, and at t equal to 0, we have these values generated. And accordingly, we have the figure generated. Of course, I did some of the work before starting this sheet. So these are the values which are known to us from our boundary and initial conditions. And now with the time step t equal to 0.01, the value can be generated, and we can write the equation in explicit form. So it is a weighted sum of the values from previous 3 points, so we get the 4th point. So our expression would be from finite difference formula, uij plus 1 would be equal to lambda times ui minus 1j plus 1 minus 2 lambda times uij plus lambda times ui plus 1j. And with lambda equal to 1, we have ui minus 1j plus or minus uij plus lambda times u plus ui plus 1j. So let's calculate. So at this point, we will use these three values at the previous time step. So they will generate a new value over here. So in explicit form, we can write. So ui minus 1j minus uij, central term, plus ui plus 1j. So please note that j step is the same. J step is the same. The x has two indices ui. The time index is j plus 1. So this expression would yield a value. Now we can repeat that one for all the x values in time. So at this time equal to 0.01, we will have the values generated. And similarly, since we have the explicit equation, therefore we can repeat that for as many times as we like. So we have accordingly the graph will be generated. So that is going to be the picture of the solution. At different times, I plotted the solution at x0 at t equal to 0.02. So these are propagation problems that propagate the solution in time. So this is FTCS demonstration in Microsoft Excel. By using FTCS, we have the explicit equation. So all the values, all the new values can be computed on the basis of previous values. You can check that one from any point. For example, at this point, so you can see that these three values are involved to compute a new value. And we can see as here that F20 only involves the points with E index. The other methods like BTCS, that is implicit type, in that case you don't have that type of formulation. In that case you have to construct the complete matrix A, and then AX equal to B type equation should be solved to get the solution at a new time step. And also in the Crank-Nicolson method, you have to go for that strategy too. So this completes our tutorial on the parabolic PDE with the method forward time, center space.